So we're now going to look at machine language. So we can see here, machine language is right on the kind of interface between the software. So we've got the software, the kind of top part, and then this kind of hardware hierarchy down in here. So the machine language, is right on this interface between hardware and software. So machine language is also known as the instruction set of the processor. And as we said, it exists right in this kind of hardware-software interface. So there's actually two different ways of looking at it. You can look at it from either a hardware aspect or a software aspect. So you could say you've got some hardware device, you've got some hardware platform, and the instruction set tells the programmer, what the hardware can do and how to interact with it. So you can say that hardware instruction set is a programmer-oriented abstraction of the hardware platform. Or you can look at it from the other side and you can say, well, someone's defined some instruction set, and then the hardware is actually the implementation of this instruction set. So there's different ways to look at it, either from a hardware side or a software side. And writing code in machine language is the lowest level coding possible. So because it exists right on this kind of hardware software interface, you cannot get any lower. If you write code in C, it's compiled down to machine language. So writing it yourself is the lowest level coding you can do. So if we look in this instruction set, it obviously contains a series of instructions, and these instruction sets typically manipulate memory. So they manipulate memory using a processor and a set of registers. So we'll now look at each of these in turn. So we're going to call memory, it's basically just a device that stores data and instructions. So it can store data and instructions. So if we just look at memory at the top level, it's just, it's got all these slots, and each slot can store different data elements or different instructions. And then each slot has got its own unique address. So if you want to access a particular word, so for a 16-bit memory, each slot will be a 16-bit word. So to access a particular word, you need to supply the address of its slot. So there's different notations we can use. We'll use this kind of square bracket type syntax, as you can see here. So you can either say memory and then in square brackets give the address, or RAM. There's different types of memory. You can say, right, I'm going to access a particular address in RAM, or this kind of M, just a shortcut, and we'll just say M square bracket syntax is referring to a particular address in memory. Now look at the processor. So this is usually called the central processing unit, or CPU, and it's capable of performing a fixed set of operations. So it can do arithmetic and logical operations, which are done using the arithmetic logic unit, or ALU, and it can also access memory. So there's various operations that allow it to access memory, read and write, and so on. And then it's got some control operations such as branching, which we'll see later. So the operands for the operations, we usually load from registers or selected memory locations. So we need to do some addition, say. We want to add two numbers together. We normally load those numbers from registers or some location in memory. And then when we've done this addition, we've got the result of this operation. So the result can either be stored in registers directly or back into selected memory locations. So we typically read the inputs to the processor essentially come from registers and selected memory locations, and then when you've done the operation, you can write the result back to either registers or a memory location. So now look at registers. Okay, it turns out actually accessing memory is quite a slow operation in the grand scheme of things. If you think about in a computer or a personal computer, PC, The memory is a completely separate device. It's a separate chip. You got your slots of you can buy slots of RAM, and they're completely separate from the CPU. So if you're reading and writing data from registers into the CPU, into the ALU inside of the CPU, it's quite a slow operation. So typically CPUs have got a small collection of registers actually inside the CPU. So there's not a lot of memory, if you will, inside the CPU, and it just allows us to store several values inside of the CPU. So this acts as very high speed local memory. So these registers are memory inside of the CPU, so it's very high speed compared to reading from RAM, or even if you think a hard disk as well, that's even slower. So by having this small amount of memory inside of the CPU, it allows the CPU to process and manipulate data very quickly and minimize this memory access, because accessing memory, accessing RAM and accessing hard drive is a very slow operation compared to actually the actual processing speed, if you will. So for example, the ARM Cortex microcontrollers, they've actually only got 13 registers inside, so each register is 4 bytes only. So 13 registers with 4 bytes inside the actual microcontroller. It's for general purpose use. So you can see that the size is very, very small compared to RAM. You might have in a PC 16 gigabytes of RAM or several terabytes hard disk. Just the fact that you got a few bytes inside of the CPU isn't a lot, but it makes the whole process much quicker. So I just want to mention about a load store architecture. So in this load store architecture, there's actually 2 types of instructions. So you've got memory access operations. So these are where we copy words from memory to registers in the CPU and vice versa. So we can read data from memory into registers and write data from registers back into the main memory. And then we've got ALU operations, which carry out these arithmetic or logical operations on the registers and store the result back in registers. So this is an important point now. So with the load store architecture, these ALU operations can only be carried out on registers and not memory locations. So you have to do you have to use the data in the registers to do the operation and store the result back in a register. You can't access RAM directly. So a RISC machine, such as the ARM Cortex microcontrollers, as I said before, most microcontrollers typically have a load store architecture. So this is different from a register memory architecture. There's usually sys machines, complex instruction set computers, which can actually get access memory directly as well as the registers.